going to discuss planes in space. Let's suppose we want to find the equation of this plane. So we're going to need two things. We need a point, and also we're going to need the normal vector. The normal vector of the plane is the vector perpendicular to the plane. So if this is the normal vector of the plane, this will be perpendicular to the plane. So it will look just like this. And of course, it's going to create that 90-degree angle. And let's call this the normal vector. So let's use n for normal. So let's say this has the component A, B, C. Now if you find 2 points on the plane, let's say here's a point on the plane, let's call it PO, and here's another point on the plane, let's call it P. So if I create a vector from here to here, now this vector and the normal vector will always be perpendicular because this vector lies on the plane and this is perpendicular to the plane. So let's suppose that our vector from P naught to P will have the following components. So if PO has the points, the coordinates XO, YO, ZO, and P has the coordinate X, Y, and Z vector from P naught to P. That's going to be X minus XO, Y minus YO, and Z minus ZO. Now, since we're saying they're perpendicular, we know that this vector PO to P dotted with the normal vector is going to be 0, because we know that from dot product, which means if I write them component-wise, so we know that PO to P, that vector has these components. So let's go ahead and write that out. So we have X minus XO, Y minus YO, and Z minus ZO. We dot this with the normal vector, which has these components. So we write down the vector and has component A, comma B, comma C. And we know this will equal to 0. Now doing this dot product, we get A times X minus XO plus B times Y minus YO plus C times Z minus ZO equals to 0. So that is our equation of the plane. Here's our first example. We want to find the equation of the plane through this point normal to that vector, which has components. You can write this also as 3, -2, -1. So that will be our A, B, and C, because that's your components of the normal vector. And this is our point, so we can call this XO, YO, ZO. So we know the equation of the plane is A times X minus XO plus B times Y minus YO plus C times Z minus ZO equals to 0. So that's the one we derived earlier. Let's plug them in. So we know A is 3, so that's 3 times X minus XO is 0. B is -2, so I'll just put a minus here. -2, Y minus YO, that's 2. And then C is -1, so -1. Z minus, also ZO is -1, so this is +1, equals to 0. So this is our equation of the plane. Now, sometimes we like to expand and just rewrite the equation. So you can go ahead and take it further by distributing. So here we distribute the 3, distribute the -2, and then distribute the -1. So we're going to get 3x. And then when you distribute the -2, you get -2y plus 4. When you distribute -1 into z and 1, you will have -z minus 1 equals to 0. And now we just like to keep x, y, and z on the same side and move the constant to the right-hand side. So you'll have 3x minus 2y minus z is equal to, so here we're going to get +3. Move it to the other side, you get -3. So that's another way you can also write the equation of the plane, where the normal vector is right here, 3, -2, and -1, as you can see it right here. Here's another example. We're going to find the equation of the plane through these 3 points. So let's suppose this is our plane. So again, the picture is off scale. Just imagine a plane right here. You want to find the equation, you're given 3 points. So we need to create 2 vectors. So let's call this point P, Q, and R. So we need a vector from P to Q and P to R. So let's say if P is here, Q is here, and R is here, we're going to find a vector from here to here and a vector from here to here. And then the normal of the plane will be perpendicular to both of these vectors. So that will be the normal vector. Now, how do we find that vector? Well, we're going to perform the cross product of those two vectors. So that's the idea with this example. So let's find the vector P to Q. So that's going to be taking Q, subtracting P. So 2 minus 1, subtracting its x components, you get 1. 0 minus 1, that's negative 1. 2 minus negative 1, that's 3. So that's the vector P to Q. And then the vector P to R will be the following. So you'll take the component of R, you're going to subtract P. So final minus initial, R minus P. So 0 minus 1, that's negative 1. Negative 2 minus 1, that's negative 3. Then 1 minus negative 1, so that would be 2. All right, so we found the two vectors. Now we perform their cross product to get the normal vector. So our normal vector N, it's going to be PQ cross PR. So if you're not familiar with the cross product, feel free to visit the link that's in the description box so that you're comfortable with this. So we're going to do, we will set up a 3x3 matrix and find its determinant. So the first row will be our standard unit vectors I, J, K. Second row is the vector P to Q. So that's 1, negative 1, and 3. The third row, we're going to put in the components for the vector P to R. So that's negative 1, negative 3, and 2. Okay, so once you have your matrix, the determinant matrix set up, now you're ready to find this vector. So this will give me, so I will have a component for the I component minus the component for the J. Lastly, we'll get the value in front of the K. So for the ith component, we're going to cross this, cross that, and we find the determinant of this 2x2 matrix. So you will do this times that, and then minus this times that. So 2 negative 1 times 2, that's negative 2, minus 3 times negative 3, that's negative 9, so put plus 9. Now for the jth, we're going to cross this, cross that, then find the determinant of that 2x2 matrix. So we're going to get 2 times 1, that's 2, minus 3 times negative 1, that'll be plus 3. And for the kth, again, we do the same thing. We cross this row and this column. So we find determinant of that particular 2x2 matrix. So you'll have negative 3 times 1, that's negative 3, minus negative 1 times negative 1, that's plus 1. Okay, so this will give us negative 2 plus 9, that's 7, I, minus, and then 2 and 3, that's 5 for J. And then for K, we're going to get negative 4. So that's what I'm going to write down here. So this is our normal vector. So this vector is perpendicular to both P to Q and P to R. So of course, it's perpendicular to the plane. And you can write this component-wise as 7, comma, negative 5, comma, negative 4. So now we're almost there. We got the normal vector. So we know this is our coefficient for A, B, and C. Now for our point, you are free to choose either of these points. You can either pick P, Q, or R. I'm going to select P. So our point would be P, which has the component 1, 1, negative 1. So the equation of the plane, we know it's A times X minus XO plus B times Y minus YO plus C times Z minus ZO equals to 0. So plug them in. So this is your XO, YO, ZO, and A, B, C are these guys right here. So we have our plane as 7 times X minus 1 plus, so B is negative 5. So I'll just put a minus 5, Y minus 1, C is negative 4, so minus 4, Z minus negative 1, so that'll be plus 1 equals to 0. So this is our equation of the plane. Now, if you want to redistribute, you can also do that. So this is 7x minus 7 minus 5 times y plus 5 minus 4z minus 4 equals to 0. So then move the constant terms to the right-hand side. So this one, and this one, we can move them to the right-hand side. So you'll have 7x minus 5y minus 4z is equal to, so let's add them up first. So 5 and negative 4, that's 1. And then plus negative 7, that's negative 6. Move it to the right-hand side, positive 6. So there you have another way of writing the equation of the plane where your x, y, and z is equal to a constant term.